In this video, we want to talk about logarithmic differentiation. Logarithmic differentiation is based on the idea from the last video where having the log applied to that stuff made doing the derivative a lot easier because we could break it up instead of having to do a product with that quantity square root like we had to do with the product rule there. Logarithmic differentiation says, hey, we can take if we had the ln of that stuff, then it can be broken apart. And so that's the idea behind logarithmic differentiation. So let's see how it works. The details of how it's developed are given in the course notes, but let's see an example of putting it together. So here we have the function f of x equals the square root of x minus 2 over 2x plus 1 to the fourth. This would be a rather painful quotient rule to do, but we're going to approach it from the perspective of logarithmic differentiation. And logarithmic differentiation might even gain more of a shine when you have multiple products or quotients, if you had multiple things being multiplied or divided. Logarithmic differentiation might even get a bigger boost to be a little bit better. But here we're going to do with these two just to see how the process works. So the first thing we do is we replace f of x with y. Replace f of x with y, and then we do ln of absolute value of both sides. So ln absolute value of y equals ln absolute value of square root of x minus 2 over 2x plus 1 to the fourth. We have to bring the absolute value in just to be safe, because we don't know if this thing here could be positive or negative. Actually, turns out this thing's only defined when x is greater than positive 2. Because of the square root, square root's always going to be positive. The bottom's raised to an even power, it's always going to be positive. So this f of x function here is actually always positive. But we use the absolute value just in case, because we may not necessarily have, a function that's going to always be positive. So we throw the absolute value in it just for care. And then we do the derivative. Well, first off, before I do the derivative, let me use my properties of logs here to break up that ln part. Have a square root in top, that's that stuff to the 1/2. So it would be ln of that stuff, so the 1/2 would come out. Absolute value gets applied inside x minus 2. In the bottom, it's minus because it's in the bottom. The exponent 4 comes out, and we have absolute value, ln absolute value of 2x plus 1. And now we apply differentiation by x to both sides. So on the left-hand side, when we do derivative of ln of absolute value of y, that's going to be 1 over y by the chain rule dy dx. On the left-hand side, we do our derivative the normal way, working with these logs. We have 1/2 ln of x minus 2. So the 1/2 is going to tag around for ln of x minus 2. X minus 2 is going to go into the bottom, and 1 is going to go into the top. And again, you might recall from the notes that ln absolute value of x is also just 1 over x as the derivative. And then that's going to be minus 4. And then 2x plus 1 goes into the bottom. Whoops. Hang on a sec. Okay, hit the wrong button here. 2x plus 1 is going to go in the bottom. Derivative of 2x plus 1 is 2. That'll go in the top. Okay, and then we're going to multiply both sides by y. We're going to multiply both sides by y. On the left-hand side, we're going to multiply by y as y. So we're just going to get dy dx. On the right-hand side, we're going to realize y is equal to this stuff. And so the stuff on the right-hand side is in terms of x. So on the right-hand side, I'm going to multiply by the original function. So we go ahead and do that. So on the left, we just get dy dx. On the right-hand side, I'm multiplying by the original function, square root of x minus 2 over 2x plus 1 to the fourth. And then I just did a little bit of cleaning up here to write that down as 1 over 2 times x minus 2 minus 8 over 2x plus 1. And then to finish off this derivative, I'm going to multiply through by the square root of x minus 2 over 2x plus 1 to the fourth. Now, if I wanted to, I could do the algebra of putting these two fractions together first, and then getting a single answer, and then multiplying through by this stuff. I could do it either way. It's really up to us. I'm just going to choose to go ahead and distribute it through. So when I distribute through here, I'm going to have a square root of x minus 2 on the top. I have x minus 2 to the first in the bottom. If I think of that in terms of exponents, this would be that stuff to the 1/2 over that stuff to the first. So when I multiply or divide, I'd have 1/2 minus 1 would be negative 1/2. So I'm going to need to have an x minus 2 to the 1/2 drop down to the bottom. And then the top is just going to stay as 1. 2 is going to be there. And then instead of having that stuff now to the first power, it's now going to be to the 1/2, because that stuff to the 1/2 crossed out with one of those things to the 1/2 in the bottom. Since that was to the first, we still have a 1/2 left. And then we're going to have the 2x plus 1 to the 4 tagging along. That'll be my first fraction. And then that's going to be minus all this stuff times 8 over that stuff. And that's actually a little easier to do. Top is just going to be 8. And that's going to have a square root of x minus 2 to go alongside of it. And then the bottom, we're going to have a 2x plus 1 to the fourth times a 2x plus 1 to the first. All right, and that's just going to become 2x plus 1 to the fifth. And so now we've done our derivative. And this is slightly less work, I think, even here, than what it would have been if we'd have done it with the quotient rule. Okay, so that's the idea of logarithmic differentiation. We're going to see another example of logarithmic differentiation in the next video, where it gives us a way to differentiate functions that actually we'd be kind of hard-pressed to figure a way to do the derivative of if they weren't, if it wasn't for logarithmic differentiation. So we'll see that in an upcoming video.